method, it's the power method. Start with the theorem. It says let A be an n times n diagonalizable matrix with dynamic eigenvalue lambda. Then there exists a non-zero vector x naught such that the sequence of vectors xk defined by. Check how we're gonna find that. X1, of course, they're gonna give you the matrix A. X1 is going to be A times x2. Then that, like, I'm just gonna give you a hint. We need to find the eigenvalue and the eigenvector. I'm gonna give you a hint here. Let's say we're gonna start with x naught. Let's say this is x naught. And we found the eigenvector here for x naught by multiplying there. We're gonna find x1. It's going to be here. By multiplying A times x naught, we found the x1, which is this is the new vector. So this is the initial one, and we found a new vector, and we're gonna keep going. X2 is going to be here. X3, this is x2. X3 is going to be here. We're gonna keep going until we reach the original vector here. You got it? So we're gonna start from point, and we're gonna keep going until we're gonna convert from both sides. It's going to be convergent to the original eigenvalue and the eigenvector. Okay? It's exactly like what we did on the previous section, but now this is a numerical method. Okay? So here's the thing: xk is going to be A times xk minus 1. So always we're going to depend about the previous point. The approach is a dynamic eigenvector of A. Here is the thing we're going to use. You're not going to see this one on the slides. I just want to make it easier on you. The dominant eigenvector, how are we going to find it? By taking the point, the initial point of the xk, and divide by the large component of xk. Like you have 3 components here. Which one is the large one? You're going to divide the whole point by this one. Okay, to find the eigenvector. To find the eigenvalue, divide x2 by x1. Okay, divide x3 by x2. It's going to be the same point, the same eigenvalue. Okay, let's check that with an example. If you've done from writing down these, it's not that much hard. So let's check here. We have the matrix A, and here's our initial vector x naught, which is 144 on 89. How are we gonna do this example? Check. I'm going to do exactly the same thing. So the first thing, what I'm going to do here, I'm going to find the eigenvector for this one. How to find the eigenvector? I just want to show you how to find the eigenvector. To find the eigenvector, we're gonna use xk divided by the large component. Which one is the large component? 144. So the eigenvalue vector for x sub 5 is going to be, take the vector and take this vector and divide it by 14489, and I'm going to write down that this, so in case you want to go back, by the large component, so it's going to be, you can check that result with me. 144 divided by 144 is going to be 1, and 89 divided by 144 is going to be 0.618. So this is the eigenvector, the dominant eigenvector with x sub 5. Now let's find x sub 6. X sub 6 is going to be a times x sub 5. Always is going to be with the previous step. So x2 is going to be a x1. Now a sub 6 is going to be a times x sub 5. Okay? So that means x sub 6 is going to be a, which is 2, 1, 1, 1 times 144 8, 9 is going to be equal x sub 6 equal going to be 3, 7, 7, and 2, 3, 3. Now let's check that. How are we going to find the eigenvector with x sub 6? Divide by the large component, which is 3, 7, 7. If you check that, it's going to be exactly the same one here. Let's check that. Let's find the eigenvector. For x sub 6 is going to be, I'm going to write down the steps in case, because it's easy to forget. Then divide by the large component, which is 3, 3, 7. Check that. It's going to be the same result. This one's going to be 1, 0.688. Eigenvector.
I'm sorry, is that 337 or 377?
377. Definitely. Now, to find the eigenvalue, what are we going to do? The eigenvalue is going to be x sub 6 divided by the previous one. So that's mean we're going to divide this one by this one. Check, if you just define one component, you're going to find the eigenvalue. Check the other number, also is going to be the eigenvalue, the same number. Okay, so I'm going to do both. That's mean the eigenvalue is going to be, I'm going to divide x sub 6 by x sub 5. X sub 6, which is 3, 7, 7, 2, 3, 3. By, that's mean I'm going to divide each component, 1, 4, 4, and 8, 9. So 3, 7, 7 divide by 1, 4, 4. How much going to be? 2.618. Yeah. And 233 divided by 89 is supposed to be also 2.618. Have to get exactly the same eigenvalue.
What if it's 2.6179?
Because they're going to ask you to round it.
Okay.
Because it's a numerical approximation, okay?
Right.
So we're not gonna get exactly the eigenvalue, you have to round it, okay? Even if you check the exactly the characteristics point, which is the determinant of a minus lambda I, if you wanna check using this one, the lambda is going to be like, you're gonna use the quadratic formula. So it's going to be like a number plus or minus square root of another number over 2, okay? Which is going to be 2.617, and you have to approximate to around it's going to be 2.618, okay? Why? Because if you get a number like with this one, 2.6, or you're gonna say, okay, maybe this is not the exact lambda, but it approximates to number 2. But sometimes you can get just a number like 5. So this is the exact lambda. Check how many steps we did. Like it's easier than the previous section. And we already know the lambda and the eigenvector is going to be 1.0. And the difference over there, we use always just an integer number, like 5, 6, 7. Here, no, it's going to be with decimals. It's easier to work with decimals. I'm not going to get exactly the eigenvalue, but I can approximate to the exact eigenvalue. Check here the number. It says 1947.500. So you see the difference between, now we can use this method when we have like this number. It's not going to have like the previous section. So I'm going to find the eigenvector for x sub 5, which is divide this one by the large component, which is 4,380. So I'm going to say 4,380.625 and 1,947.500. So you need to forget, divide by the large component, which is 4,380.625. It's going to be 1. And here it's going to be 0.444, but I'm going to round it to 5. This is a point here. This is a point. So this is the eigenvector for x sub 5. Now let's find x sub 6, which is a times x sub 5. So x sub 6 is going to be a, the matrix A, which is 5.5 and 4.523 times 4,000 x sub 5, which is 4,380, and 625, and here 1,947.500. Let's mean x sub 5 is going to be how much you got?
First number is 32,807.
32,857. Okay. Point
1,875.
1,875. You see how big this number? Imagine you're working on the previous section. And the second number is going to be 14,603.75. So this is x sub 5. Sorry, x sub 6. Let's find the eigenvector for x sub 6, which is going to divide these two numbers by the large component, which is 32857. So it's going to be 1, and here it's going to be 0.44, also round this number to 5. Which is exactly the same eigenvector here. Let's find the lambda. Find the eigen value. Just going to divide x sub 5, divide by x sub 6, divided by x sub 5. That means going to be, I'm going to divide this number by this one. So 33, 2, 8, 5, 7.1875 divide by x sub 5, which is this number, 4,380.625. How much is going to be here? I'm going to divide the second number here with x sub 6 by here, which is 4,603.75 divided by 1947.5. You got that up here?
Seven point 501.
501. So 7 point, let's take 2 digit. So 50. Okay. What about the other one? The 7 point, I think 449, 499. 99. So what do you think? How much is going to be the exact eigenvalue? Check the both eigenvalue here. Approaches to which point? Approaches to 7.5. So both sides approaches, because you can round this number also to 7.5. To 7.5. That's meaning lambda is going to be 7.5. Again, if you use the exact method, for this example, 100%, lambda is going to be 7.5. Okay. So this one. Now I need to write down these steps. If there is no initial point, how are we going to work on it? You're going to do exactly the same thing here. The same thing here. Here's the matrix A with the eigenvalue lambda 1. The first step, I'm going to say x naught equal y naught. You're going to start with the certain point, like 1, 1, 0, 0, okay? And y is going to be the same x naught. Be the initial vector in Rn whose last component is 1. Largest component is 1. That means you can't start with 0, 0. Okay, you have to make one of these components equal 1. This is very important because you're gonna pick up your start point, okay? To find the eigenvalue. So pick up any vector, but the large component is 1. So at least you're gonna say 1, 0. If with R3, you're gonna say 1, 0, 0. Okay. Now the second step, we're going to repeat this one a lot. So we have to create a table. Repeat the following steps for k equal 1, 2, 3, and keep going. We're going to compute xk by multiplying the matrix A with the yk minus 1. So here is the first thing. We're going to create a table like this. I'm going to make it easier for you. So you're going to So here it's going to be the K. This is the initial K. 1, 2, like this. Okay. Here is X sub K. And here is Y sub K. We're already going to assume an initial point here, like the vector 1, 0. X naught equal Y naught. So the same initial point is going to be here. Okay? Because that's what they say. How are we gonna find X sub K here? How are we gonna find it? By multiplying A by the previous Y sub K. By multiplying A by the previous Y sub K. Okay? We're gonna check that with an example. It's going to be easier. Now, let Nk be the component of, okay, let Nk be the component of X sub K with the largest absolute value. It's also important because this is the lambda. This is the lambda here. Let's go back here. This table. I'm going to say, here's M sub K. For example, they say, let M sub K be the component of M of X sub K with the largest absolute value. Here is X sub K. Where is the largest absolute value here? It's going to be 1. That's me. M is going to be 1 here. This one is going to be the lambda, because we're going to keep going. We're going to take more than one iteration, okay? And you will see when we're going to stop, when it's going to be repeat exactly the same value. Like for example, you will see there's going to be 1.99, then go back 2.1. 1.99, 2.1. That's mean the eigenvalue is going to be 2. Because we're going to keep going around the number 2, okay? You're going to stop. They say the eigenvalue is going to be 2. Now, how to find, we already have this X here. How to find Y sub K? You're going to say 1 divided by M sub K and times by X sub K. This one is going to be the eigenvector. Okay? And this one is going to be the eigenvalue. This is just in general. We're going to do an example for these steps. You have to help me with that. So you see, that's what they're going to ask you. I think there's only one example when you do the online assignment like this. They're going to give you the A, and it's going to give you the initial vector. But here I'm going to start using this one as an initial point, okay? 1, 0. Because always they're telling you, let X not be the Y not be the initial vector, which is the largest component, is 1. So you have to include 1. You can't start with 0, 0. That's me. I'm going to say this vector is X sub naught, and it's going to be 1, 0. Y sub K also is going to be 1, 0. And M sub K is going to be the large exponent, which is 1. Now, check what I did here. I wrote down these because we're going to use it. Now, 1. They're telling you to find this X sub K, the new X sub K, that's mean X sub 1. We're going to multiply A by Y K minus 1. That's mean we have to multiply A by this matrix. We're going to multiply A by 1, 0. So it's going to be, check this result for me, 1, 2. If you multiply A, can you check it?
Yeah, that's right.
Yes, 1, 2. Here's the important thing. Check it. What it says about M sub K? B, the component of this, with large absolute value, which is what? Which one is going to be 2? That's me now. The new lambda is 2. Okay. How I'm gonna find y sub k? I'm gonna divide x sub k by 2. I'm gonna divide, you see, 1 over 2 times this one. That's meaning you're gonna divide this one by 2. So it's going to be 0.5 and 1. Now we've done it from this one. We're gonna keep going. I need to find the new x sub k. That's mean x sub 2. How? By multiplying a times y2 minus 1, which is y1. So it's going to be a times this vector. Tell me how much it's going to be. It's going to be 1 times 1.5 and 1. Now, what's the new lambda? The new lambda is 1.5. Now check here the difference between these. We are on 2 and we are on 1.5. That's mean the actual, the exact lambda between 2 and 1.5. We're gonna keep going, okay? We're gonna compare to the actual eigenvalue, from the exact eigenvalue. Now, how to find the new y? We're going to divide these two numbers by 1.5. So 1.5 divided by 1.5 is going to be 1. And 1 divided by 1.5 is going to be 0.6666. Keep going. I'm just going to say 0.67. Okay, let's keep going. Let's find x sub 3. We're going to multiply a times y sub 2. We're going to multiply a by y sub 2. So it's going to be 1.67, and here is going to be 2. Is that right? What's the lambda here? M sub k, M sub 3 is going to be 2. And divide these two numbers by 2. This one is going to be 1. 1.67 divided by 2 is going to be 0.834. You can see it.
I'm sorry, how do we determine what the new M sub k is?
Which one? M sub k?
Yes.
It's the largest
Oh, okay.
number from these.
Gotcha. Okay.
Okay?
Thank you.
It's important, yeah, if you have a question, ask, because it's like simple steps, but you're gonna do mistakes.
Thank you.
It's 0.834. Okay? Check, we still have between 1.5 and 2. Let's find x sub 4. We're gonna multiply a times y sub 3. It's going to be what? 1.834, let's do 35, okay? And here 1.67.
Would be two, no, it's 2 times.
So which one is the larger? It's 1.83. Because I round this one, so I'm gonna make it 5. Okay. You see now, instead of 1.5, it's going to be 1.8. That's mean we're getting closer to the number 2. How to find y sub k and divide these two numbers by? You got it? You don't know how to do it?
Oh, okay, I'm sorry. You
Kinda?
divided by M sub k.
Which one? M sub k,
Yeah.
which is the largest number from these two.
Yes.
Now we're going to divide to find y sub k. We're going to divide these two numbers by 1.835. So it's going to be 1 here, and here is going to be what?
0.9.
0.911. Did you round?
Yes.
Let's keep going. X sub 5. We're going to multiply a by y sub 3. So how much is going to be? .91. And it's going to be 2. So M sub k is going to be 2. And divide these two numbers by 2 to find the y sub 5. 2 divided by 2 is going to be 1. 1.91 divided by 2, 0.95. I'm rounding the number, okay? Check now. Between 1.8 and 2. Let's check the number 7, x sub 6. We're gonna multiply a times y sub 5. So it'll be 1.95 and 1.91. You get exactly the same numbers? Keep in your mind, this is the eigenvector, and here is the lambda. Now, what's the lambda here? 1.95. Check now, this number is closer down to the number 2, right? So now we are between 2 and 1.95. How to find the eigenvector here, y sub k? Divide these two numbers by 1.95. So it's going to be 1 and 0.98. Let's keep going here, the last one. Yes or no? You got it?
Yes.
Now to find x sub 7, we're going to multiply a times y sub 6. So it's going to be 1.98 and here's going to be 1. Where here?
It's 2 times 1 plus 0.
So it's going to be 2. Maybe I missed this. the lambda number is going to be there. It's going to be 2. Now here, because you see 2, 2, 2, that's been here, it's going to be also 2. Because we move it around the vector left or right until we arrive to the actual vector, okay? Now we're going to divide these numbers by 2. So it's going to be here, the first one, 0.99. And here is going to be 1. Now tell me, check the numbers here. This is the eigenvector here, and this is the lambda. Check the numbers here. Approaches to which one? To 1. Approaches to what? To 1. So the eigenvector is 1, 1. Tell me these two numbers here, the eigenvalue approaches to which one? To 2. So the lambda is 2. You got it? So you just have to know when we're going to stop. The difference now, if you do another iteration, number 8, you will get 1.99 here. That's mean we're going to closer to 2. I don't have to do another 1. I'm just going to go lambda is 2, the eigenvector is going to be 1, 1.
But this whole time we haven't, in y sub k, we haven't exceeded 1, and in k, we haven't exceeded 2. So,
Oh, yeah.
so that's,
We never passed the 2. You're
Right.
right. For this example, but another example, you will see the eigenvector, you jumping around a certain number, and the eigenvalue, you jumping around a certain number until you reach, okay, you can say this. Like the example, the previous one is 7.5.
Right.
If you do it with the long way, it's going to be 7, 6.5, and keep going until you reach 7.5, which is in the middle, okay?
So how would you know at what point to stop at?
When you see the difference here, on the test, I'm going to tell you when you're going to stop, like 3 iteration of 5, okay? And then you're going to tell me the eigenvalue and the eigenvectors. But when you're going to stop, check the difference between these. This is the eigenvector, and this is the eigenvalue. You see, it's 1, and here is 0.99. So this is converges to 1. This is 0.98 converges to a 1, and this is 1. That's mean the eigenvector is going to be 1, 1. On this case, check the lambda. 1.95, which is converges to 2, and here is 2. That's mean we're going to say the lambda is going to be 2. Okay?
Okay.